Hello, welcome to another problem session. So today we're going to do some standard problems, application of Ampere's law, and Ampere's applied to cylindrical symmetry problems. So we're going to learn about what this thing is called cylindrical symmetry, and these are the two problems we're going to do. We're going to do another cylindrical symmetry problem later, not today, maybe next video. But this is a classic problem. You have a infinitely long wire which carries a steady current I, and we want to have a magnetic field at a point P, which is a distance S away from the wire when you measure perpendicular from the wire. Okay. And then there is this, which is application of what you find over here, and superposition using two wires now. So this wire goes up, and this is also considered infinite. This is infinite, and this is also infinite. That's why this there's no break in the wire, but that just signifies this gone on for a long distance. And then this infinite this side, infinite this side, and this one is infinite this side and infinite this side. Okay. And then we're supposed to find magnetic field at a point between the two wires, and they're actually kind of an opposite direction here. I could have done same direction, this opposite direction, just for having a more variety. And their distance d apart. It could be like a kind of like a cable, right? I mean, if you look at any of those strips of wire that you have in your household, there's one current goes this way and the current comes back this way. So there's a point between. So S1 is a point between, and S2 is a point outside. The speed is a point outside, and the distance between the two wires is d. So we're supposed to find magnetic field here, magnetic field over here. Okay. So if you know how to do this problem, you probably already know the answer to the problem in P. For A, answer for A, that B is the direction is a right-hand rule. You use thumb along the wire and you rotate around. That's coming from Biot-Savart law. So direction is coming from the Biot-Savart law, and that's going to be perpendicular, and in this diagram is going to be going in the picture. So that's the direction. That's the direction, and magnitude is now mu naught over 4 pi 2 pi s I. So this is going to be this is going to be the magnetic field magnitude, and this is going to be direction for A. And B is going to be a little bit more, it's going to have two terms, one from this and one from this. Okay, so how do we get this answer? Okay, so if you know how to do it, maybe you want to do this problem out first, and then you can do this also out and come back and check my solution. Okay. Okay, now I'm going to do it using Ampere's law. Okay, you can do it using Biot-Savart law, and I've done it in a previous video. So I'm going to do it using Ampere's law. So I'm going to use Ampere's law. Okay. So Ampere's law is this. Okay. Is you do a circulation of a magnetic field in a oriented loop, around some loop of this quantity, magnetic field dot dl, and when you're done doing it, is going to be equal to mu naught times current that got enclosed by this. So if I do like a loop like this, or any loop, you can do loop like this. So let's do loop like this, and then you do this integral on the left side. So this is C around this, and the dl is, that's the dl vector, a small element on the loop in the direction in which you have defined the orientation of the loop. And then you look at how much current actually went through it. So if the current is going through it, so this will be a positive current going through it. So if I take a right hand loop, so this is because of this direction, this is positive direction. So if this is current will be, say this is I1. So the I1 will be positive when enclosed. And then suppose I have another current which goes in the other direction, let's say I2. So then I enclosed will be, this will become plus because of this orientation due to this loop direction, and this will become negative because of the same orientation. So I1, it will be I1 minus I2 in this formula, and then do this integral like that. Okay, now B, notice B is inside the integral, and if you can't solve for B unless B can come outside this integral. But this is the only time B will come out is there's some special situations. All right. So the loop has to be chosen properly so that this becomes somehow B at some B which does not change on the loop. Maybe on the loops it's got the same value at B. So B same at all points of loop times length of the loop. So if this becomes this, then this B being same, that will mean I am able to actually get the B magnitude just by solving this simple algebra equation. All right, so that's the trick. Okay, so how do I make sure the B is the same? How so there has to be some argument. So let's look at this. So if I have an infinite wire, so this infinite wire, and if I look at a point P, so if you look at so this is point S. So there is a element here, and there's look at the corresponding element here. So when you do the integral, Biot-Savart law, so Biot-Savart law will be like this. So look at this, I'm doing Ampere's law, but I'm going to use something from Biot-Savart law. Okay, and that Biot-Savart law is that B at P has the following character. It's going to be mu naught I over 4 pi, and I got to integrate over the current. Okay, so current circuit. So not this one, but the current carrying, and I need to do dl. This dl is on the current circuit cross u hat dl to point P over r dl to point P square. So this is Biot-Savart law, and we've done several problems in Biot-Savart law. You should go ahead and study them. Okay, now I don't need to do this problem when I'm applying Ampere's law, but I need to get some sense of what it will be like. So this one and this one are same distance away. So say this is, say, distance z, and and this is also same z, same distance, okay, or maybe distance d and distance d from this, let's call it some O, from P to O perpendicular this point, okay. So if you look at right hand rule, from there you can see the this cross this is going to be inside the inside, magnetic field will be pointed that way. From here to here, magnetic field will be pointed that way. And all of this, always the magnetic field is pointed into this. So, and this is not a very special point. It's just arbitrary point, and it's pointed in there. So on the right side, if I'm on the left side, I use the same right hand rule. Is, say, if I go the distance s away on this side, then over here magnetic field is the B over here will be coming out, and so it says like B is kind of circulate, B will circulate. Another thing I notice is because of the symmetry, it can not depend on this. This is going all the way to infinity, this is going all the way to infinity, so it can't depend on the direction from this to here, because there is no unique point P along this direction. So if this was the z-axis, it cannot depend on z. So because this P and this P is an identical situation, because this current carrying wire is going to infinity. So I can just displace along the z. This P, P1, P2, all of this are going to have same amount of magnetic field, same magnitude of magnetic field, which means if I go in a circle around here, at all these points of the circle, all points of this circle same magnitude of B, right? Same magnitude magnetic field at this point circle. Just direction is changing from place to place. And so if I this is due to the cylindrical symmetry of the current carrying wire. Because the cylindrical symmetry of the current carrying wire, two things have happened. All these points have been same distance, and magnetic field is not dependent on the direction, and magnitude is not dependent on direction. So let me erase some of this. So cylindrical symmetry of current, not for other things, current. Because of cylindrical current, Biot-Savart law says, Biot-Savart law says one thing is B, if I write down X, Y, Z, independent of Z, because the current is along the z-axis, okay? Another thing we can say, the magnitude of B magnitude only dependent on the square root of x square plus y square, not on direction in xy plane. And third thing I can say is B has direction, B at some point P has direction along using right hand rule. So if this was the z-axis, and say I call this x-axis and call this y-axis, over that y I have a so BP has a direction along phi, u hat phi, unit direction phi, or phi hat. Okay, so it has a direction which we say is x direction over here, y direction over here, and at any place here is the phi, u hat phi direction. So this is the angle phi. So it's u hat phi depends on the polar angle phi is minus sine phi I hat plus cosine phi j hat. So this is the direction. Okay. Let me erase and kind of summarize these things and how I'm going to use for choosing Ampere's law. Okay. Okay, so I cleaned up and had this summary of what we found from applying Biot-Savart arguments, right? So we want to apply now. We want to find what B will be. Okay, to find B of S. Okay, so that's what the task is now. That's the task. So this task is we're just looking for a magnitude because I already got the direction using Biot-Savart law. So I'm going to use Ampere's law. Now this dl is different than dl we originally used, and this mu naught is there's no 4 pi over here, and this is not all but just charge enclosed. So because this is at all for this thing, I'm going to use a circle in this xy plane. So at all points B will have the same value. And when we do this integral, this thing, the dl, so this dl is s times d phi and the unit vector phi, and b is b at s, it just depends on s, u hat phi, and they're the same, so dot product gives me 1, and so this thing just becomes b dot dl. You have a b of s times d phi, and now this is the integration, and in this circle I'm going all the way around, so that means it's going to be 2 pi 0 to 2 pi, and so I can already see that this side is just going to be, this is not depends on phi, this doesn't depend on phi, and so this whole thing becomes 2 pi s b at distance s. From how about the right side? For the right side, I ask a question. See, this is the area that's enclosed. Has any current going and which direction? So I use right hand rule. So that tells me the direction here is, this is the positive direction. So the current is going in that direction will be positive. And so over here, this is actually equal to just positive I. So together, you can see that B magnitude is equal to mu naught I over 2 pi s. So we got the magnitude here, and we got the direction here. So got the direction from Biot-Savart law, and magnitude we got from Ampere's law. So this is a classic problem and it illustrates in a very basic way the entire set of arguments you need to apply to Ampere's law to a problem. So once we have solved this problem, we can use the solution of this problem to solve where the cylindrical symmetry doesn't exist. Okay, but we can use a superposition, and that's the part B here. Okay, so for part B, you can see clearly there is no cylindrical symmetry for both the wires together, right? So, but if I work one wire at a time, then there is cylindrical symmetry. So let's look at a P1. So this is a cylindrical symmetry. So this is going to be at P1. Let's call this I1. I'm going to call this I2. So there will be B1 vector from this guy, and then there will be B2 vector from this current, and so B at P1, so this will be B at P1. And let's draw. So this is the current going up, and this is current going down. See, what's the B1? Let's see in terms of direction. I use a right-hand rule. So it's B1. B1 has a direction into the, like a back of the arrow going back, right? And this one is also going back. If I go do this, and this also going back. This one is also going back. So they are going to add vectorially, and their magnitudes will also add. So if I take a if I take a coordinate system, z and x is coming out, and y is like this. So this is all with respect to that. They'll be all at this point all towards negative x axis. What's the magnitude will be? That will B1 will depend on that distance S1, and this one will be D minus S1 from there. So answer for B at P1 will be minus I hat, that's the direction for both of them, and B1, okay, mu naught I over 2 pi S1 plus mu naught I over 2 pi D minus S1. So this is just a minus I hat mu naught I over 2 pi 1 over S1 plus 1 over D minus S1. So you can say that combine them, minus I hat mu naught I over 2 pi D over S1 D minus S1. So that's the answer for that point. How about if I had a point on the other side, point over here? So this distance is S2, then this distance is D plus S2. Oh, not D, S2 minus D is S2 minus D. That's so silly. From here to here is 2, from here to here is D. Okay. Now we need to know, it's going to be again B1 from here, again using right hand rule, B1 is into the board. How about B2? B2 is actually coming out of the board. B2 is coming out of the board. So using the same coordinate system, so this is going to plus I hat and this is minus I hat. So we will get B at P2 will be let's use same kind of stuff. I hat mu naught I over 2 pi. S2 is going to B2 will go in the positive direction, so 1 over S2 minus D plus 1 over S2. Oh, minus actually, this is minus 1 over S2. So that's the answer for this. So although there is no cylindrical symmetry when the two wires are looked as one system, but I can use one system at a time, and I can use superposition principle to actually get the answer for the combined system from the individual system. Okay, I haven't done the problem of a thick wire, so thick wire problems will come next. Okay, all right. Okay, just a reminder that if you haven't subscribed, I appreciate if you can subscribe to this channel. It helps the channel grow. Okay, and if you like this kind of explanation, please hit the like button. That also helps the circulation. And if you like this kind of explanation of physics, kind of very direct mathematical analysis without kind of putting a lot of things under, shoving a lot of things under the rug, you may want to go check out my textbook, which is on this website. It's used by a lot of places right now. So this is a freely available textbook. Take care. With that, yep, take care and bye.